One of the guaranteed problems that will show up on the complex analysis qualifying exam, or the combined analysis portion, but the complex analysis portion has a contour integral in it. So I thought I'd take a moment to talk about what a contour integral is if you're not familiar with it. I'm not going to go into super great detail, but I do want to take that practice test here shortly, and I need to review my contour integrals. So let's start with the usual calculus integral. Many of you, I'm sure, have taken calculus before if you're watching this channel. But the idea is we have this function. This function maps real numbers to real numbers. We have an x-axis, we have a y-axis. And we look at the interval from a to b. And if you're familiar with calculus, you'll know that if we integrate fx dx from a to b, we get the area under the curve. Area of the shaded region. Now, integrals are very useful and they're very powerful because they tell us some amazing things, like the area under the curve. They're not exclusive to that though, because integrals can also be used to calculate the length of a curve through 2D space, 3D space, really n-dimensional space if you want. And if you're a physics student, they can be used to calculate work on an object. They can be used to calculate the mass of a object that doesn't have uniform density. Maybe the density of the object is described by some weird function. I don't know. There's a lot of applications with integrals. And if I had to describe integration to someone that's never had calculus before or is very bad at math, and I'm trying to avoid the mathematical definition the best I can, I would say that integrals study the idea of adding up infinitely many infinitesimally small objects, if you want to call it that. Because that's essentially what this integral is, right? We have, if you're familiar with the definition, we approximate this area with tiny rectangles, but the more rectangles you add, the smaller they get, and they approach the area under the curve. Or at least that's the way we define it for the Riemann integral. The Lebesgue integral is a little bit more abstract, and then you can even get more abstract than that when you get into measure theory. But I'm going to avoid that in this video because I really just want to talk about how to take this idea and extend it into the complex plane. So that's what I'm going to do here. Okay, so we draw the complex plane in a very screwed up manner. Can't draw straight lines. But this is the complex plane. Maybe I'll label it C over here. And it's tempting to think that you just want to draw this down here, but you can't do that. It's not the same thing. Because here you have two real axes. Your function up here takes real numbers and returns real numbers. So it takes numbers on the x-axis and gives you numbers on the y-axis. But for functions down here, you take in numbers on the complex plane and it returns numbers in the complex plane. You can think of a function of complex variables as like it's moving the points around in some way. You can think of it that way. But there's no real nice, at least not at the time being, a nice geometrical interpretation. Like up here, this is pretty reasonable, right? You look at this and go, oh, okay, it's obvious what I'm doing. I'm figuring out what this area is. But down here, it's not the same because you could get a complex number as your integral. And what does that have to do with area? I mean, imagine a square that has area square root -1. It's kind of weird to think about. But the idea is still the same, right? How the integral is defined. So let's just take a moment to look at this and say, okay, so what is my analog of the interval a to b down here? You know, how do I take this and move it down here? Well, over here it's an interval, but in the complex plane it could be anywhere, right? But it might look something like this. You know, this might be my interval in quotation marks. And you know what I'm going to do? I'm going to call that endpoint ZA, and I'll call this point ZB. And there's a reason why I call it that. I call it that because I can think of ZT as a parameterization of my curve. So my curve can be thought of as like a function of the interval AB. That means that if I plug in A into my function, I'm going to get this point. If I plug in B into my function, I'll get this point. And if I plug in T between A and B, it's basically just going to trace this curve. So when I start at A and work my way up to B throughout the interval, it essentially traces this contour. Now the contour doesn't have to be like closed, for example. What I really mean is, here I don't have any breaks, but I don't necessarily have to have 0 breaks. It might be like piecewise smooth or piecewise continuous. I don't know, whatever you want to call it. I'd rather not get into those details. I'm just trying to think of a simple contour, or a simple closed curve. Not closed, I shouldn't say closed, but a simple curve in the complex plane. It is possible that ZA could coincide with ZB, in which case we call it a closed curve. It could also double back over on itself, you know, make a figure 8 or something, in which case interesting things can happen. But that's essentially the idea. This is sort of acting as our interval that we integrate over, and we have some function defined on it. And then we have the integral of fz dz. And typically what people in complex analysis like to do is that they'll name the curve. Gamma seems to be a popular name. So they write gamma down there at the bottom. So we integrate the function fz, whatever it is, dz, over the curve gamma. Now, it might be difficult to integrate along this curve if it's kind of weird looking. So what they do is they do like a U substitution almost. Because it's not really a U substitution, but they just use their brain for a second and say, okay, z is a function of t. So I can rewrite this integral as an integral of t. So we have f of z of t. And then I want to put my dt here, but I have to be careful because z is a function of t. So if I find dz dt, that gives me like z prime of t, whatever that derivative is. And so dz will look like z prime t dt. And then this is what I have to put over here. So we end up with z prime t dt. But now I have an integral with respect to t. So now I'm integrating from a to b. And if I know this parameterization up here, then I'm in good shape. This would be another way of evaluating this integral. Because this is basically a real integral, right? Well, okay, it's not a real integral. Because you're still integrating on it, but you're integrating over an interval, which is familiar. That's what I'm really trying to say. All right. So without going into more detail, I figured I would do at least some problems that I was looking at. So what would be a good one? Let's start with something really stupid, really basic and simple, because I like the easy problems. I don't like being challenged. I get challenged every day. How about, all right, here's some examples I was looking at. Okay, how about this? We have the integral from 0 to pi over 4 e to the it dt. Okay. Now, if you're not super familiar with contour integrals, or not contour integrals, complex analysis, this might be kind of scary because you got that I up in the top. But just know that e to the it, that gives you a point on the unit disk in the complex plane. And that t represents the angle formed with the x-axis. So if I were to draw a picture, it would look like this. So here's my unit disk in the complex plane, real, imaginary. So e to the it are points on the circle, and the t represents the angle. So we start at 0 down here, which means that we start here and we go up to pi over 4, and pi over 4 is this halfway part. So my curve, essentially, that I'm integrating over is that bit there. So in a way, actually not in a way, exactly, this is a parameterization, like what I've done here. So it's fairly simple to integrate. You treat it just like a regular integral. So you have negative I e to the it plus my constant. We evaluate from 0 to pi over 4. The constant cancels. Now, okay, I have to say some things because when I wrote this, some of you may have cringed a little bit. When I took calculus, there's always that dreaded C that calc students forget. And they get points taken off at the end because they always forget the plus C. And I made sure that I never forgot that plus C. So I put it everywhere, even when I had a definite integral. When you have a definite integral, you don't have to write it. And some people complain at me when I write it. But I keep it because it's just the way that I learned it. It's muscle memory at this point. I don't think about it anymore. But if I plug in, but what I do is I just cross it out as soon as I write it down. And it bothers me if I don't write it. So that's all I'm doing there. Okay, so now we plug in stuff. So what do we get? We get negative I e I pi over 4 minus, but that minus becomes plus I e to the I times 0. I is just a number. I mean, if I put 2 up here, it would have come down in front. It's just when people see I, they get a little bit queasy. But it's a number just like any other number. Okay, so now what? Well, e to the 0 is 1 because anything to the 0 power is 1 with the exception of 0. And the I is left over, so we leave the I alone. But what about e to the I pi over 4? What is this number here? Well, remember, that's just square root 2 over 2, comma, square root 2 over 2 in R2. So if I want to write this in the complex plane, it would be negative I square root 2 over 2 plus I square root 2 over 2. And then we have the plus I here. So that part canceled. Or it became 1. So I'll write 1 here. And now I can clean it up. So I have negative I square root 2 over 2 plus square root 2 over 2 plus I. And then if I want to make sure I didn't screw up, I'll write my real part here, plus I, and then I have a 1 minus square root 2 over 2. And that should be my final answer. So let me double check my work to make sure I didn't mess anything up. I tend to do that a lot these days, just screw up everything. So the negative I retains, and then the negative I times I gives me a positive 1. So that makes sense. And then I combine real parts, and then I combine imaginary parts. So it looks like I've done it correctly. I got this out of the Churchill Brown book, by the way. easy example. All right, so now there's two more examples I want to do. And one of them is an illustration of my favorite theorem from complex analysis. I just wish I had paper. I'm always using scrap paper. You would be surprised at just how much scrap paper I use. I probably use way more scrap paper than anyone else. Okay, so what's the example? Let's say that this is my function. I'm going to define something terrible, but not too terrible. What am I saying? Let's keep things complex numbered. Oh, z to the z. I don't think that would be too bad. Okay, so we have something pretty nasty looking. And let's say that I want to integrate over this guy. We'll call it gamma, big gamma. And I want to calculate this integral over this gamma. So I want to integral gamma fz dz. If I understand my favorite theorem as well as I do, which isn't very well, then I notice two things. This is a closed curve, and I have a function that's analytic in the entire complex plane. Since this is analytic everywhere, I know it's analytic in a neighborhood that surrounds big gamma, then I can use a very important theorem called the Cauchy-Goursat theorem to solve this problem in 2 seconds. And I use those 2 seconds to write down the answer on the paper. The answer is going to be 0. This is by the Cauchy-Goursat theorem. Cauchy-Goursat. There. The Cauchy-Goursat theorem essentially says, well, I'm just repeating myself, but if you have a closed curve like this, and you have a function, analytic function, that's, it's a function that's analytic in a neighborhood that surrounds gamma, then when you integrate on that curve, you're going to get 0. And the reason it's my favorite theorem is because the result sounds too good to be true, because this analytic function could be nuts. But, and your curve could also be nuts. You know, you could have something nutty here and nutty here, yet when you integrate it, it turns out to be 0 every time. And I thought that was kind of an amazing result because it sounds too good to be true. But the more you think about it, the more it makes sense, right? Because if you think of gamma as, your analog to the interval from calculus, you start at one point of the interval or on this curve, and then you wrap around, and eventually you return to where you start. Well, if you integrate from the interval a to b, and then you backtrack from b back to a, and stop where you started, when you go the other direction, you're basically eating up all of the area under the curve when you went from a to b. So in a way, getting the answer 0 kind of makes sense here. So that's why it's my favorite theorem. It's a pretty powerful result. And I believe depending on which book you read, there's a variety of different proofs for it. And a lot of the times they build up to it. They'll start with like triangles or discs, and maybe in some books they go to the rectangle. There's a bunch of different proofs for it that are usually shown in textbooks. The one that I learned was the one that used the triangle. But I believe the Churchill book does it differently. Anyway, so that's the Cauchy-Goursat theorem. Correct me if I screwed this up and I lied to you. This z to the z scares me. I don't know why. You know what? Let's just get rid of it. It's bugging me. Let's say z to the e power. I don't know. That's kind of stupid, but it's z to some constant power, so I'm less scared of it. Wait a minute. Man, I really suck at complex analysis. I don't know why I'm scared of it. I just am, so I'm just going to get rid of it. Write 16z. The other stuff I'm not scared of, so I'm just going to write 16z. The reason I'm scared of it is because analytic has, like, you can represent it as a Taylor series expansion. So I have to be a little bit careful with my exponents. So, yeah, so if I had time to talk about analytic functions more, I would. But for the time being, I'm just going to leave it as polynomial times e to the z. Okay, so what's the last example? The last example is one of my favorites. We have integral modulus z equal 1 dz over z. Okay, why is this example, or why is this integral important? It's important because we can't use the Cauchy-Goursat theorem here. Cauchy-Goursat theorem requires your function to be analytic in the region containing the curve. But here, our curve is modulus z equal 1, which is a circle. It's a circle of radius 1 centered at the origin. But the function is 1 over z. 1 over z is not analytic in the inside the circle, because if I draw it this way, so let's say this is here's my complex plane, here's 0, here's my curve that I wish to integrate over. Well, if I have a region containing the curve, and I call the region omega, in a lot of textbooks they use omega, this function 1 over z is not analytic because it has a pole or a singularity at 0. When you have a pole or a singularity at 0, bad things happen. Well, okay, bad things happen. I should be careful with the way I say things. You don't get 0 up here. You can't apply the Cauchy-Goursat theorem. So we have to be careful with this curve. We're going to get some answer that's not 0 in the end because it's not analytic. So let's figure it out. Well, what can we say? We can parameterize the curve and write z theta is equal to e to the I theta, which means that dz is equal to the derivative of that with respect to theta, so I get I e to the I theta d theta. And then we substitute. So when we substitute, we are integrating from 0 to 2 pi. Remember, e to the I theta is just a point along the curve. So when you start at 0, you start down here. And then as theta runs from 0 to 2 theta, you start to wind around the circle. And then when you hit 2 theta, you get back to where you start. So we integrate from 0 to 2 pi. We put dz in the top. So I have e to the I theta d theta. And then we divide by z, which is e to the I theta. So this is equal to this. But we get some really nice cancellation. And then the I can pop out. So we have I integral 0 2 pi d theta. And this integral is really nice to figure out. It's just going to be equal to 2 pi. So I end up with 2 pi I. So we got an answer that wasn't equal to 0. There is a way to calculate integrals where you have singularities inside the curves, and then the number of times that you wrap around the curve also matters too, because then it can grow larger. And it also matters in what direction you go around the curve in too. Those are what's called winding numbers that you need to calculate, but I'm not going to go into that here. Perhaps in a future video I'll talk more about contour integrals, because I want to make videos about me studying for this upcoming qual, and contour integrals are basically going to be an entire series in and of themselves. There's also this thing called the residue theorem. So what we've essentially done here is calculated a residue. But again, I don't want to talk about that because that takes too much time. Anyway, so this is sort of a brief introduction to some contour integrals. I gave you, if you want to look up Cauchy-Goursat theorem and residue theorem and the Cauchy integral formulas, be my guest. But these were just some basic rudimentary examples that I like, and I hope you guys appreciate it too. Anyway, thank you for watching, and thank you for subbing to my channel. It means a lot.